afternoon. Let me first go through a very brief review of what we did in the last lecture. Then I'll pause for questions, okay? I hope you can think some questions where I review what we did in the first lecture. I think the most important equations that we used in the last lecture is really this equation listed here. Vg equal to VFB plus oxide voltage plus the surface potential. When you look at this equation, I hope you think about the energy band diagram. You know, why any difference between Vg and VFB has to be taken up by a voltage drop, a band bending in the oxide, or a voltage drop, band bending in the substrate. Okay. The Vox term can be replaced by minus Qs over Cox. Qs is the charge on the capacitor. Cox is the capacitance. So Q over C is the charge. Minus sign has to do with the fact that we take the voltage from the gate, but we take the charge from the substrate. Right? Now applying this equation, then we review the definition of a threshold. That is the point when the surface potential is equal to 2 phi b, or 2 times kT over Q log Na over Ni. Now, when phi s is equal to 2 phi b, what is the corresponding gate voltage? That corresponding gate voltage at phi s equal to 2 phi b is called a Vt. And that must be equal to VFB, that's the first term, plus phi s. Phi s is equal to 2 phi b, plus or minus Qs over Cox. And that gives us this last term. Okay? So that's what we did review the last time. And this is actually also a little bit of a review, so let me just go through this before I ask you if you have questions. If we make a plot of the substrate charge as a function of Vg, using this as a way of reviewing our understanding of the 3 regions in this Vg scale, we know there are 3 regions separated by 2 points. The starting point is the flat band voltage. If the bias deviates from the flat band voltage, we are either in accumulation or in depletion. And then what separates the depletion and the inversion regions is a point called threshold voltage, Vt. All right? So let's see if we can make this plot. The substrate charge as function of Vg. Now we know at flat band condition there's no substrate charge. Is that right? We're assuming there are no fixed oxide charge. We'll throw those in later. And when we are in the accumulation, we just have a capacitor, except this Q and V, the linear relationship between Q and V is offset by a voltage called VFB. In other words, the charge, in this case, accumulation, is, as always the case, minus Cox Vg minus VFB. Right? So charge Qs is equal to minus C Vg, except V is offset by a voltage called VFB. In the accumulation region, we know that as we move Vg away from the flat band voltage, the surface potential is going to increase, band bending increases, X depletion increases, therefore the depletion charge increases. So most of this, at least in the first order model, all of this is the depletion charge. You may call this the depletion charge, yeah, depletion layer charge. When Vg equals to Vt, we reach the point phi s equal to 2 phi b. At that point, or beyond that point, xd doesn't increase anymore. Xd saturates at xd max, and therefore the depletion charge also saturates. That's the started line. The depletion charge does not increase anymore because depletion region width does not widen anymore. On top of the depletion charge, however, we now have a second component to the substrate charge. We call that inversion charge. That's because we have inversion layer. There are now electrons in the inversion layer. And that charge also increases or is equal to Cox minus Cox Vg minus Vt. Right? So again, we see a Q equal to Cv relationship. This time the V is offset by the threshold voltage. And altogether, we have the solid curve. Right? Qs as function of Vg. Finally, one thing that we often talk about is the capacitance. This Ox is a mistake. We should take this away, correct this. That is, the capacitance is, by definition, dQs dVg. Rather than Qs over Vg, we always talk about small signal capacitance, not only in MOS capacitor. In fact, even with PN junctions, we usually talk about small signal capacitance. So here, the capacitance we're dealing with is small signal capacitance. You know, capacitance, if we talk about large signal capacitance, would be Qs over Vg, right? You already know what minus is about. It's because we're taking the voltage and charge from opposite plates of the capacitor. In small signal capacitance, we just take differential, dq dV, and that's what we have. Since we already know Qs is function of Vg from the left-hand side curve, we can simply plot the slope of this curve, and that becomes our capacitance, C. Okay? Now, for example, the slope in the accumulation region is a constant equal to Cox. That's why we say capacitance is constant Cox. In the depletion region, we notice capacitance or the slope gradually decreases, and capacitance decreases. And in the accumulation region, the slope increases again. In the inversion layer, the slope increases back to Cox. That's the slope, and we can see the CV curve drops to, or increases to Cox. Right? So this is a summary of what we covered in the last lecture. Any questions? Any questions about the last lecture? Yes?
You said...
Thanks for using that microphone.
Yeah. At the bottom there you wrote minus Cox quantity Vg minus V what? Is that a T?
Yes, T.
Okay.
Threshold voltage, Vt. Good. All right. Okay, actually, someone asked me the question after the last lecture. He asked me, what is the Fermi level in the oxide in a MOS energy band diagram? You know, we drew energy diagram, for example, I just arbitrarily draw one right now like that. There's a Fermi level in the substrate. Let's say there's Fermi level in the gate. What about a Fermi level in the oxide? Or to take an even simpler case, the so-called flat band case. Yeah, or flat band case here, or Fermi level in the substrate, or Fermi level in the gate, and there's a voltage difference. What about the Fermi level in the oxide? Shouldn't we pay some attention to it? Well, it turns out the Fermi level in the oxide does not have any real significance. As a result, we don't pay attention to it. Fermi level has an impact on electronics through this relationship. That is N equal to NC exponential minus EC minus EF over KT. So in the oxide, this is the EC. And EF is always quite small, quite low, below that EC by several EV, right? And as a result, you can see electron density in the oxide is supposed to be very small. So that's consistent to that extent. But you know, suppose this EF is 1 EV below EC. Do you know what number will come out for this? Do you happen to know what that would be? Well, if it's 1 EV, if EC is 1 EV below EF, It's essentially asking us what is the electron concentration in a p-type silicon, right? Because there the difference between EC and EF is about 1 eV. Is that right? Yeah? Yes? In a fairly heavily doped piece of silicon, what is the electron, p-type silicon? What is electron concentration? Your answer probably will be, maybe 100 per cubic centimeter, right? Because MP product should be about 10 to the 20th. Yeah? Yes? Absolutely right. So if Fermi level is 3 eV below EC, remember this barrier height is 3.1 eV. We're talking about something like, 10 to the minus, 10 to the minus 50, 60 per cubic centimeter. Is there any meaning to this number? Obviously, it's a meaningless number, right? It means really doesn't matter whether Fermi level is here, is here, is here. Really makes no difference. That's why we don't talk about the Fermi level in the oxide. Okay? Put another way, wherever Fermi level has to lie, it's acceptable. It doesn't contradict any relationship that has to be followed. Okay? That's why we don't have to worry about the Fermi level. If you, however, draw a Fermi level here, if there's a situation where you have to draw a Fermi level here, you have to really think about it. What does that mean? Does that make sense? All right? You have a question?
I'm just wondering about in the insulator, the Fermi Dirac distribution is still valid.
Yes, 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 that's right. Okay. Other questions? Or if not, we'll start a new section, a continuation of the analysis of the MOS system. But this is a more quantitative analysis of the MOS system, and it's the topic of section 3.3 in the textbook. Right? What we will be doing is one way of describing the goal of this is to say that we're going to derive an equation for the CV relationship. It will be a continuous relationship that we will find. All right? It's not going to be piecewise continuous, separated between inversion and accumulation and depletion regions. We're going to see some subtleties from this more quantitative analysis. Right? So the starting point is the Poisson equation. Well, before we talk about Poisson equation, we'll talk about charge density. What we're going to do is we're going to solve this potential as a function of a location. We'll call this x. We'll solve phi as function of x. Very much like the way you have done for the p-n junction analysis, all right? Except the analysis, of course, will be more complicated because here we cannot assume there's nothing but ionized impurity. In fact, there often will be holes if it's in accumulation. There may be electrons if we're in the inversion regime. Is that right? That's what makes this analysis difficult. Okay. So let's review what is the hole density. It's possible we're going to have holes if we're in the accumulation regime. Hole density we know is always equal to P naught, equilibrium concentration, exponential minus Q phi over KT. This comes from the relationship that P is exponential function of EC, or rather EF minus EV, I guess in this case. I'll do it this way. Is this relationship. So anytime this EV moves away from the Fermi level, by 60 millivolt, the whole concentration will decrease by a factor of 10. And that's relationship captured here. For example, look at the special case of phi equal to 0. Phi equal to 0 refers to the case in the neutral region of the substrate. We call that point phi equal to 0. At x equal to infinity, phi is equal to 0. So in the neutral region. In the neutral region, when phi is equal to 0, we know the whole concentration just equal to the equilibrium concentration of the substrate. Is that right? So we know that part is right. And any time when phi is not equal to 0, we know that whole concentration will be modified by this relationship. How do we know that? It's from this relationship that we used the last time. Is that right? Every time phi is not 0, meaning there's a band bending, then the spacing between EV and EF has changed, and therefore the whole concentration will change exponentially. Okay? All right. So make sure we understand notation. This is the whole density at any location x is equal to the equilibrium concentration, which basically is the doping concentration, exponential minus phi x over kt. Let's remember, phi as function x is what we're going to try to solve by solving the Poisson's equation, right? All right. And to simplify this, we call this P naught exponential minus beta over phi x, which is following the textbook convention. And beta is defined as q over kt. It's a trivial substitution just so that we don't have to carry this q over kt. Instead, we'll carry beta. Okay? All right. Next, what about the electron concentration? Well, that's very similar to the first equation. Electron concentration will be equal to n naught, equilibrium concentration of electrons, roughly speaking, is ni squared over na. Is that right? Why do I call this roughly speaking, by the way? Why do I say it's roughly speaking n naught is equal to ni squared over na? Under what condition would the electron concentration not be equal to ni squared over na? What's that? High temperature is a good answer, and probably a more conventional way of stating that is to say intrinsic semiconductor, right? But in most cases, this is a good approximation. The fact is that we're not even making that approximation. That's why I want to call this out. This is example. If it's heavily doped p-type semiconductor, n naught is equal to ni squared over na. If it is an n-type semiconductor, n naught will be approximately equal to nd, right? And in intrinsic semiconductor, you also know there's an n naught. So in any case, always going to be n naught. And anytime phi deviates from 0, n will increase or decrease relative to n naught by this exponential term. All right? So it's very general so far. Okay, next, I'm just giving you a suggestion when you read. Skip to 3.3.4. If I ask you to skip, it's because I think if you did not skip, what material in between may be even more confusing than helpful. Otherwise, I will let you read it as a reading material. You can always decide you don't need to read that because you already know a part. But when I ask you to skip, it's because I think it's better to not to read that part. So let's just go to section 3.3.4, equation 336. All right, let's just do that. And now we're ready to write down the Poisson's equation, second derivative of the potential phi with respect to x is equal to minus rho over epsilon, right? That's the standard Poisson's equation. Rho is a function of x. Why? Because phi is a function of x. That's why rho will be a function of x, right? Rho is always equal to minus q times the whole concentration, whole carries positive charge, plus ionize the donor density, right? When donors ionize, carry positive charge, minus electron concentration, electrons carry negative charge, and minus ionized acceptor concentration, right? Okay. And next, we're substituting the earlier equations for P and N in here. Now it looks quite complicated because minus Q over epsilon S, parenthesis, P naught exponential minus beta phi, minus N naught exponential beta phi, minus Na and Na, and plus Nd. It's okay how you see exponential beta phi came into this equation? It's through this P and N term, right? Okay? All right, so at this point, we're still solving a differential equation, right? That's what we're doing. But it's a difficult differential equation to solve. There's no simple way of solving it. So what we're going to do is we're going to play a trick and simplify this equation to try to solve it. What we're going to do is we're going to apply a chain rule and make this substitution. All right. Now maybe we need something in between. I'll see. All right. Second derivative phi with respect to x is equal to 1/2 d phi dx square. Let's see if we can verify this together. All right. Let's look at the right hand side. This is just math, just calculus. There's no physics involved. Let's see what we can see. Let's look at the right hand side. Right hand side is 1/2 d phi of a variable. Call this whole thing the parenthesis with the square as a variable, right? Okay. So how do you make this do this differentiation? Isn't it correct that you're going to say it's equal to 2? 2 is because of that. Yeah. Call this y squared, if you will, right? So 2 times y, that will be d phi dx. Is that right? Yeah? And why don't I just do it this way? d phi dx. Is that right? Yes? Yeah? And through chain rule, we know, well, first of all, these 1/2 and 2 cancels out, and this cancels out. So what we have is we have d square phi dx squared. Is that right? Correct? Okay. So that's why this is a mathematical identity here. All right? Okay. So what we have done is we have changed the left-hand side of the equation that we built in the previous slide. The right-hand side has not been changed at all, remains the same. Take another look at the right-hand side. This is what we saw at the bottom of the previous slide. Is that correct? All right. Okay. Now, why is this helpful? Because what we're going to do next is going to integrate both the left-hand side, the new left-hand side now, and the right-hand side with respect to phi. Now, for example, the right-hand side, when we integrate with respect to phi, we get this integral, right? So we're going to deal with integral later. Let's look at the new left-hand side. If we integrate with respect to phi, what do we end up with? We end up with this. Is that right? Okay. Maybe I jumped this a little bit. All right. The first thing we did, actually, is we multiplied the 2 to both sides. So the right-hand side now has a 2. You see? We did not have a 2 in front of q. Now we have a 2. It's because we multiplied this 2 to the right-hand side. Okay? Next, we integrate with respect to d phi to phi. So we end up with just d phi dx squared for the left-hand side. Okay? You see what we just did? We integrate this with respect to d phi. Yeah? Yes? So we have to, therefore, integrate this with respect to d phi. All right? Integrate right-hand side. And that's exactly what's written down here on the right-hand side. Yeah? Minus 2q over epsilon s, this whole parenthesis, being integrated with respect to phi. Okay? All right, next. Continue with the mathematics. We can just integrate it. Turns out it's quite easy. In fact, let's just do a one step in between. Let's see, why don't we integrate this term together? All right, what do we get? Integrate with respect to phi. Don't you agree it will be p naught? And it's going to be, let's see, how would that be? It's going to be minus 1 over beta. All right? Exponential minus beta phi, and phi will be taken at 2 limits, 0 and phi. Is that correct? All right. So let's see if, well, let's just write this down further out. So this is minus beta p naught over beta exponential minus beta phi, and then minus this again with phi replaced by 0. When we replace phi with 0, we end up with 1. Yeah? Yes? So it's really plus p naught over beta. Right? Or put another way, would be equal to minus p naught over beta exponential minus beta phi minus 1. All right? Okay? Do we find these two terms in what we wrote in the slide? Okay, first of all, this 1 over beta has been taken out here, 1 over beta. All right? So we see the minus P naught, exponential minus beta phi. That's the exponential minus beta phi, yes? There's a minus 1 term, and that's a minus 1 term, yeah? Where do you think this term comes from? Well, it came from the integration of these, all right? That gave us the P naught, okay? Is that right? Okay. All right? In fact, let me remind you, even here, we did not make the approximation that P naught is equal to NA, because this is not always correct, right? For example, in intrinsic semiconductor, P naught would not be equal to NA or N-type semiconductor. We actually did not even make this assumption. What we did is that we said that the minus NA plus ND is equal to minus P naught plus N naught. That is always true. At equilibrium, because of charge neutrality, the ionized acceptor charge plus the ionized donor charge, we did not even assume whether this is P-type or N-type, must be equal to minus of the whole charge plus the electron charge. Follow what I'm saying? Right? Because positive charge, negative charge must agree. So we didn't even assume this is P-type or N-type. Okay? So that's where these two terms come from. It's because we have those two terms. We have those two terms, therefore we have a P naught term, we have an N naught term. Okay, any questions about this step? You're still with me? All right. Okay, next. This is unusual in solving differential equation. We did not manage to solve this differential equation, but we managed to find a analytical expression for the square of the differential, square of d phi dx. So we're going to take the square root of both sides. The left-hand side becomes d phi dx. Right-hand side becomes this quantity put in the square root sign. Is it okay? All right. Now we're back to the more sort of conventional, familiar territory. Presumably at this point, all I have to do is we'll put x on the right-hand side, divide this whole bracket to the right-hand side, and try to integrate left-hand side, right? Right? Unfortunately, if you try to do that, you're going to find you cannot integrate this, and you cannot find the answer from a table of integrals either. This just cannot be integrated analytically, unfortunately. All right? So what do? Well, if we want to integrate this numerically, of course, it's very easy. Everyone can do that with any kind of math application you can do. But turns out there's no reason for us to do that. Even though we say at the beginning, we said that we are trying to find phi as function of x, but actually we don't. We don't need to know phi as function of x. It really doesn't help us. All we need to know is to find Qs, right? That's what will give us the charge. That's what we want. That's what gives us the capacitance. We don't really need to know the potential at every point. So we want to get something that gives us Qs. Now it's very interesting that Qs is related to the electric field at the surface. Let's first look at this relationship, if it's true or not. In other words, Qs is related to d phi dx, electric field. We actually don't need to know phi. All we need to know is d phi dx, because that's electric field. Electric field will give us Q. Let's see if you recall this relationship. What we're talking about really is just Gauss law. You know, if we take Gauss law, whatever this situation is, whether we have accumulation layer here or inversion layer or whatever, if we use Gauss law, do you agree that we can write that the electric field at the surface, how should I say this? Yeah, the electric field at the surface, let's call it E at, how do I do it? I'm looking for a place to write easily. E at 0, right? Electric field right at the surface. Do you agree is equal to charge in the substrate divided by epsilon s? Do you agree? That's Gauss law. In this case, I'm plotting the Gauss box right at the interface. not in the oxide, but on the silicon side of the interface. Right? You agree? If I draw the Gauss box with box right at the silicon side of the interface, then the electric field at 0 at surface is equal to Qs. Qs is all the charge here, including any inversion charge and any accumulation charge. Are you with me? Right? Divided by epsilon s. I have to admit that I don't recall whether there should be positive sign or negative sign in this Gauss law. Can you help me? If we say, well, okay. All right. The first thing is we have to declare what we consider as the positive electric field direction, right? Okay, let's try to do this. Let's say this is the positive x direction. So I guess we have to define the positive electric field direction as this direction. Is that right? Okay. And I remember the relationship is that the electric flux going out of the box is equal to charge in the box, right? Right? And so I must have a negative sign here, yeah, because we're defining the electric field going in as positive rather than electric field going out as positive, yeah. Okay. Sign in cases like this is not important. At least we don't have to memorize, fortunately, because if you ended up with a positive sign by mistake, when you come to the end of the problem, you will find, it's non-physical. I just changed the sign. So I do that all the time. If I did this in this lecture, I hope you will bear with me. When you really have to be careful about a sign is if this is not only term on one side, but there's another plus quantity, let's say f. Now you are in trouble, right? You better be sure you got this two sign right, because you will never be able to figure out you have a non-physical answer just from the sign, right? So in this case, it's not too important, but I think we just figured it out as negative, all right? All right. And so since all we want is Qs, that's really what we want, so all we want is electric field. And we already have it, electric field. You see, we don't have to do that integration to get phi anymore. d phi dx already electric field. Isn't that right? Yes? Yeah. Specifically, d phi dx is equal to minus of electric field. You remember, this is a relationship between field and the potential, right? Field is equal to minus dv dx, or d phi dx. So we already have this electric field. That's wonderful, and that's going to give us the charge. So we'll just move on from there. All right. Okay. So the electric field at the surface is, we use this notation E at x equal to 0, right? E at 0. We can use another notation, which is a little easier, that is a subscript S to represent surface. Okay? So electric field at the surface, that's called a ES. Now this relationship between Qs and ES, that is Qs is equal to minus epsilon s times ES by Gauss law. Is that right? And we already know Ex, fortunately. That is equal to epsilon s d phi dx. Evaluate that differential at the surface. And therefore it's equal to epsilon s d phi dx, and evaluate that expression at phi equal to phi s. Let's think what that means. We want to evaluate this differential at surface. Is that right? Yes? Yeah? Evaluate x equal to 0. But the expression we have for that d phi dx is not a function of x. I'm going back to the previous slide. It's not a function of x on the right-hand side. It's a function of phi. So what is phi equal to at x equal to 0? What should we evaluate this phi at in order to get the surface electric field? What is phi equal to at x equal to 0? It's equal to phi s, isn't it? That's the notation we introduced in the last lecture, right? The potential at the surface is called surface potential. It's phi s. Questions? Yes? All right. So all we have to do is to replace the phi of this expression with phi s. That's what we did. Now you notice all the phi's have been replaced by phi s. Do you see that? These four quantities used to be phi. Now they are phi s. Speaking to the microphone, please.
Okay. In the previous slide.
Previous one. You like to see
Yeah,
this slide?
Yeah, you
Okay.
integrate the square term from the bulk to the surface, right? The d phi over dx square.
I increase that?
Integrate
Integrate.
from the
In
bulk
order to obtain this equation,
Yeah.
we did make an integration.
from the bulk to the surface. Is that right?
We didn't even say surface. Let's be careful. Let's go one step further, all right? That's slide number 3. Yeah, here we are. Let's see what integration we were doing. We integrate from 0 to phi. So in that sense, we did not integrate from 0 means x to infinity. When phi equal to 0 is x to infinity. By putting the upper limit as phi means we did not integrating all the way to x equal to 0, to the surface. If we did that, we could have, or would have, or could have put phi sub s here. Is that right? By not putting phi sub s here means we did not integrate all the way to the surface. Okay? But it's a good observation, interesting observation, because we already pointed out, admitted that we actually don't need okay, I'll just leave it at that. I suppose it is better not to integrate the surface. So as a result, we have preserved the fact that this is valid at every point, so we have the electric field at every point, except we don't know this electric field as function of x. All we know is we know this electric field at phi at that point. For example, if we want to know the electric field at the surface, we have to replace this phi by phi s, right? Of course, right now we don't know what phi s is either. Right? For example, if I give you a Vg equal to 2 volts, we don't know what phi s is yet, but we're going to figure out what phi s later as function of Vg. So for now, let's just be satisfied that we know the electric field, and therefore the charge is a function of the potential of the surface, phi s. All right? And that's where we are right now. Okay? And when I put down equation number, that's equation number in the textbook, so that you can relate the lecture to the textbook. Okay? All right, let's look at this one more time, this equation, and feel very comfortable what we're dealing with here. What we're saying is that we now have expression for the substrate charge density. Let's remember, I don't call this surface charge density, I call it substrate charge density, right? Because this could include the depletion layer charge, all the charge in the substrate, right? We know the substrate charge as a function of the surface potential, right? Complicated function, but it's a function. It's an analytical function of surface potential. Is it okay? All right? All right. And we know that because by using this Gauss law, and any charge in this below the interface is related to the electric field at interface. Okay? So here we are. Okay? And when we say the QS here, we actually included inversion charge, depletion charge, as well as accumulation charge. Okay? All right. Good. Next, you remember CS is defined. In fact, we can really say defined or equal to, either way. It's equal to minus dQs d phi s. Or maybe we didn't do that. Sorry, I should define this for you. Sorry about that. This is not, we have not seen this before. This is a new concept. The concept is the following. You know, you have all been, you are all familiar with this picture. I'll redraw this picture. That MOS capacitor can be defined, not defined, can be represented as two capacitors in series, Cox and well, we usually don't have a name for it. I'll give a name in a minute. And you say, this is Vg. This will be our ground, a neutral part of the substrate. Right? I'd like you now to focus on this point here. What is this point? If you don't think of this as equivalent circuit, you think of this as the representation of the physical structure. There's a very physical interpretation of this point here, this electrical node. That is the potential, that is this interface. So the voltage here would be the interface potential, phi s. Do you see what I'm saying? All right? Yes? So for the oxide capacitor, for example, sits between Vg and phi s, Vg and phi s. Whereas the substrate capacitance, I'm going to define now a capacitance called a substrate capacitance, sits between the surface potential and the ground. Is that right? So if you treat this box, treat this as a black box, you don't know what's inside. You don't know we're talking about a MOS system. All you know is that if you change the potential here, you have to supply this surface, supply into this lead some charge. If you change the potential at the surface, you have to supply some charge through this electrical lead. If you find such a black box, what would you call this black box? Do you call that resistor, inductor, or a capacitor? It's a capacitor. That's why I want you to think about it, all right? Don't think of this physically as some depletion layer or what. It's much more general concept than that. If you have to supply charge in order to change the potential at a point in the device, you're dealing with a capacitance, all right? And what's the value of the capacitance? It's the ratio or differential of that charge you have to supply with respect to the potential of that terminal. So dQs, d phi s is the substrate capacitor, a substrate capacitance. That's probably a new term for you. So let's just agree to call this capacitance substrate capacitance, CS. All right? Okay? So don't think we're just representing the depletion layer capacitance. Not at all. This is going to represent inversion charge capacitance, going to represent the accumulation charge capacitance. Can you agree with this idea? That just because we have to supply a QS in order to change phi s, or vice versa, therefore we have a capacitor at hand, and we call that capacitance CS. Is it okay? Okay with you? All right. So what is CS then? Well, we can simply differentiate this expression QS with respect to phi s, dQs, d phi s, and we already know QS is function of phi s, so we'll just differentiate it. Is that right? Yeah? For example, right-hand side, you can see where it came from. When you differentiate a quantity, let's say 1 to the minus 1/2 power, what would you get? Well, first you're going to get a 1/2 multiplied to the to this, and that's why this 2 in the numerator gets shifted to the denominator, right? That's because it's 1/2. And then we're going to put a e to the y to the minus 1/2 power, and that's this term here. You see, we brought that same square root into the denominator now. Is that right? That's y to the minus 1/2 term. Get it? All right. So the numerator, of course, is only the differential of what's inside the square bracket. Is that right? Okay? So I don't think we have to go through each term here, but you know, just pick one term, you will see it's there. Let's pick a simpler term, pick this term. Right, this term, P naught beta phi s. When you differentiate with respect to phi s, what do you get? P naught beta phi s term. When you differentiate that term with respect to phi s, what would you get? P naught beta. Right? Do we have that here? Well, you see the P naught. You don't see the you see the 1 here. That's the P naught. You don't see the beta. What happened to the beta? Beta got taken out into this. That's why beta is moved from the denominator into the numerator. You see that? Okay? So that's what it is. Okay? All right. So the numerators come from differentiating that. All right? Do you have it? All right. Great. And that pretty much is the end of this mathematics. From this point on, we'll talk about the physics of this. All right? So your chance to ask about the mathematics here or the derivation. Any questions about this, what we did? We have now found a relationship between the capacitance, the substrate capacitance, not the total capacitance C yet, but you know it's trivial to change C to get C from CS. All you have to do is to put CS in series with a constant Cox, right? So that part is trivial. So we have done the non-trivial part is find the CS. CS is expressed as function of phi s. I admit we don't know what phi s is yet. We're going to fill that gap later on. But let's right now pretend we know phi s. So now we have CS as function phi s. That's okay? All right. Now for simplicity, it can be shown, this is not in the textbook, but I'll just write down for you, that can be rewritten, these terms can be rewritten in terms of the electron concentration at the surface called NS, hole concentration at the surface PS, and the doping concentration NA and ND. All right? It's not too surprising we can do that because you know, for example, PS is equal to P naught exponential minus beta, equal to P naught exponential minus beta phi S. That's the surface hole concentration. Yeah, we in fact use that when we start to build the Poisson equation today. We review that hole concentration at every point is equal to the equilibrium concentration exponential minus beta times the potential at that point. So at the surface, then we simply put potential at the surface here. Yeah, for example. So this last step is really just substitute PS and S for those exponential terms. It just looks a little simpler, looks a little perhaps a little less intimidating, but it's really exactly the same thing, these two expressions. Okay? All right. So it's useful, we will see, because sometimes it's easier to use this second expression than the first one. Okay, so now we move on to look at this, what we have done, what we have derived. The best way to do that is look at a few special cases. All right? So let's look at a special case. What is CS at Vg equal to Vt? Let's look at that special case. What is CS equal to at the threshold voltage? What is in this equivalent circuit? What is CS equal to? Look at the equivalent circuit at threshold voltage. Okay? We're going to get the answer from this. But before we do that, I'd like to just ask you for some, just some fun, and say, what do you think it is, based on either what you know before or what if you have a new guess because of the analysis today. I don't expect you to have that. Feel free to bring that up. What do you think is CS equal to at Vg equal to Vt at the threshold point? What do you think it is? All right. This indeed is a problem from that piecewise model, and we just move away from that. The piecewise model would say that there's a sudden jump at Vg equal to Vt. Is that right? Yeah? If you look at this point, well, first of all, look at this point. If you look at this point, CS really is equal to C depletion. In other words, we have the depletion capacitance in series with Cox. Yes? That's this point. Yes? If you look at that point, it's actually approximation. It says Cox is equal to infinity. Because if CS is equal to infinity, of course, the total C of these two capacitors in series is equal to what? Cox. Is that right? Okay. So those would be the two answers that I thought you might give me. And both of them, of course, are not totally correct. And we're going to see what is the correct answer now. All right? Okay. What is the correct answer? I want to know CS. Evaluate that at Vg equal to Vt. Well, they are expressed in terms of phi s. So what is phi s equal to at Vt? At Vg equal to Vt at threshold. Phi s equal to what? 2 phi b. Great. So if you want to use the first expression, just substitute this with 2 phi b, right? It's actually a little easier to use the second expression, because you all have concept what is hole concentration at threshold, what is electron concentration at threshold, for example, right? Let's remember the example we have been using is N-type, P-type doped example, right? P-type doped example. Let's continue to use that example. So because it's P-type doped, at threshold, what is the surface concentration of the holes? Remember, it's inversion now, right? Inversion. We start with P-type substrate. Now we have inverted the surface. So P is probably approximately 0, right? The PS is approximately 0. Is that correct? Are you following? Do you agree? Yes? And what is NS approximately equal to? Pardon me? Okay, will be equal to okay. Let's see. Okay, roughly equal to NA. Is that right? Very good. And Na is Na. And let's keep the problem simple, saying there's only acceptor in the substrate. There's no donors, right? Because we're using p-type as example. Is that correct? So just take this away. So the numerator becomes what? Minus Na minus Na, in other words, minus 2Na. Is that correct? So do you see what gets 2Na here? Is that right? Yeah? And we take the absolute sign. I did not make a note of that. That's because we're taking the square root here. When you take square root, you always have a choice of plus minus based on physics. Based on physics, we know capacitance is always positive. All right? That's why we take the absolute sign. Is it okay? All right. So we got a 2Na here from numerator. Do you agree? So let's see what we get from the denominator, shall we? Also quickly, all right? Let's say PS is about 0, NS is Na, and this ND we say it's 0, right? And initial equilibrium hole concentration is basically negligible. Is that right? Yeah? Okay, then we have this beta phi s minus 1. Now, what do we know about phi s? What is phi s equal to at the threshold condition? It's 2 phi b, isn't that right? Yes? Yeah? 2 phi b minus 1, okay? 2 phi b minus 1, okay? 2 beta phi b minus 1. And we can show that the minus 1 is negligible. Let's just call it 2 beta phi b, approximately speaking. Okay? So what do we get? We get a 2 here. We get a 2. Beta, we got it here. Phi b, we got it here, right? And Na, we got it here. Let's see. Okay, what happened to this Na? This Na and that minus Na get canceled out. You see that? Na and minus Na. So I thought this minus 1 is negligible. It actually cancels out this Na. Is it okay? So minus 1 times Na cancels out this Na. Yeah? So what we have is this term here. You see that? Are you following this step? Okay, great. That's it. So all we have to do now is simplify this mass, eliminate some common terms, and I guess you'll take my word for it. It will be this. All right? So we'll not spend on this step. Instead, I want you to spend some time on the next step. After we simplify the simplest form, I'm going to make it more complicated. All right? I'm going to force the denominator. I want to put this term in the denominator. I'll tell you, in fact, why I do that. Because this term is d max. All right? So I'll force, a lot of this term has to do with xd max. I'll force this term, put this on the denominator, and see whatever is left over, I'll put in the numerator. So let's review this what's in the denominator here, so if you agree. This is the expression for depletion region thickness. If you remember, depletion region thickness is always equal to, well, I guess there's a 2 somewhere, so there's a problem. We'll deal with that, okay? But anyway, so pretend we have a 2, or maybe instead of pretending, I'll put this way. All right, I'll do this. X depletion, what is X depletion, or XD max, all right? At the threshold is equal to XD max. And what is that equal to? You probably would agree that is equal to 2, no, I got this wrong, sorry. XD max is equal to, let me see. Yeah, that's right. It's equal to 2, sorry, I'm trying to think what that is equal to divided by this. Yeah, that's right, for being here. Okay, this is correct. It's a 2 epsilon s times 2 phi b divided by QNA. Do you agree that's the expression for the depletion thickness, depletion layer thickness? Very good, all right? And so what I'm doing, and therefore it's equal to, I'll take a 2 out, 2 times epsilon s phi b over QNA, all right? So I compared this with what I have here. We don't have the 2, so I'll forget about 2 for now. But I have everything else. Therefore, I put this quantity in the denominator, right? That's that, okay? So what's missing then? If you see that, I got everything right. N is in the right place, Q is in the right place, epsilon is in the right place. I'm sorry, epsilon is not. Phi b is in the right place. By right place, I mean it's in the denominator, so I kept the denominator. The epsilon is in the wrong place. It should be in the numerator, but here we had it in the denominator. All right, so we have to put an epsilon in the numerator. Okay, all right. Next step, you have already seen the denominator is nothing but xd max divided by 2. You see, xd max divided by 2. Right, so we have the epsilon. Hey, now here's interesting now. So what is the answer? You got the answer now. How would you say this in English? Right, this mathematically we see that CS is equal to this. So what is the answer? The answer is CS is the capacitor corresponding to half the thickness of xd max. In other words, it's not the Cx. It's twice as large as the Cx. You see what I'm saying? Yeah? This is really interesting. It's really mathematically straightforward. We see that. Why is that? Why is the Cs larger than the capacitor due to the depletion layer alone? Well, that's because we have two components of charge. One is the charge due to the depletion layer charge, and that gives us the one capacitance. We have another charge component that due to the inversion charge. Remember, charge is made of three parts. It's made of depletion charge, made of inversion charge, and made of accumulation charge. In this particular example, the third component truly is negligible. But neither of the first two terms is negligible, right? So we have to bring them in. And the first term, when we differentiate that, we're going to get the usual, what you would expect, epsilon s over xd max. So that concept is not wrong. What you have in mind is correct, that the depletion layer will give us capacitance. The value is epsilon s over xd max, and that's just fine. What's new is that the second term will also give us a capacitance. You probably have already had this uncomfortable feeling before. That is, how could we assume there's no electron at this threshold point? You know, we already said the concentration is equal to the doping concentration. That doesn't seem to be that small electron density. And indeed, it's not negligible. This term is fairly significant. All right? So we have to consider that in the capacitance. So what is the capacitance this contribute? It contributes this much, dq inversion d phi s. And if you carry that out, it happens to be the same amount as this at the threshold voltage. And that's why the total capacitance is twice as large as due to the depletion layer alone. Following what I'm saying? Right? Following what we're saying? Okay? All right. So you may ask, why at that point, at the threshold point, the inversion layer charge happened to contribute exactly the same capacitance as the depletion layer charge? Why at that point, this, in fact, let me introduce a notation name now. Let's just call this inversion layer capacitance. That's what I want to call this. All right, let's call this inversion charge capacitance or call this inversion layer capacitance. Doesn't matter. This is a new component of capacitance you should remember. It's in parallel with the depletion capacitance. It's called inversion layer capacitance. All right. So the question is, I think worth thinking is, why is the inversion layer capacitance at threshold condition happen to be exactly equal to the depletion layer capacitance? Why is that? Anyone want to venture an answer?
Is that just how they decided to is that how they decided to define the threshold voltage?
Wonderful. That's the perfect answer. Right? The last time we already talked a little bit about how do you define VT. Why did you pick that definition? There's many ways you can decide when the surface is inverted, right? Why do we pick that particular situation? The best justification is exactly this. That is, if VG is larger than that, most of the changing VG, applied change in the gate voltage, additional voltage, will be used to change inversion charge. when VG is less than VT, the response to the changing voltage is not in a change in Q inversion, but in a change in Q depletion. Do you see what we're saying? So that actually is a good way to define the where the inversion takes place. Yes.
Would you talk about why you chose a minus sign, like you have CS equals minus DQS d phi s?
Yes.
And also like you'll have C inversion equals minus DQ inversion d phi s.
Great.
And I would like to talk about that.
Oh, all right. The relationship between this this equation and how do we then relate that fact to these in terms of capacitance? Is that right? Okay, wonderful. Pardon me? Oh, why the minus sign? I see, that's the question. The minus sign is always there because of this relationship. Okay, minus sign does not have to do with the fact that there are three components to the surface charge, to the substrate charge. Minus sign comes from the fact that Q is always equal to minus C times V, or differentiate by V, well, okay, C times V, that's fine. Or C is always equal to minus dQ dV. Doesn't matter what we're dealing with depletion charge or accumulation layer charge or depletion layer charge. And the minus sign comes from the fact that we're taking the voltage from the top electrode of the capacitor, the gate. We define that as our voltage, our positive voltage. Whereas we take the charge from the substrate. Q is taken from the substrate. When we do that, we have to introduce negative sign in this relationship between capacitance, charge, and voltage. That's all. All right? Is that a question or that's not a question?
Yeah, but you're not taking the voltage from the gate. You're taking the voltage from the surface of the semiconductor.
Great. Let's look at the semiconductor. Now we're talking about this capacitor now. In this capacitor, the surface is the top electrode. Where's the bottom electrode? Bottom electrode is the ground, if you will. So we're still taking the voltage from the top electrode of CS, and we're taking the charge from the bottom electrode. The charge, everything's the bottom electrode. Go.
But that doesn't work when you have an inversion charge. The inversion charge is on this. So you would think that would be a positive sign, and you think the signs would cancel out.
Right, right. This comes from the fact that you are, maybe it's not, maybe it is, but even if that's not what you're asking, I think it's worth pointing out in this concept of thinking of the surface as a real physical electrode, and how to visualize the, in fact I'll do it this way. What I've just plotted is I'm writing down a few positive signs to represent the charge in the depletion layer and region, and wrote down some charge negative sign as the charge in immersion layer. All right. I want you to remember that when we say we take the substrate, the capacitance CS, all right. The top of CS is not the immersion layer. That's not our capacitance. It's actually even on top of that inversion layer. Okay, all right. It's a mathematical boundary that we're using as the beginning point of our capacitor. And all these, both the inversion layer, accumulation layer, as well as the depletion layer, is part of our bottom electrode. Bottom electrode. All right? Okay? So let's remember, when I talk about a surface electrode, when we talk about surface potential, I am excluding the charge in the inversion layer. That belongs to part of the bottom electrode. Okay? All right. So the electrode itself is just mathematical plane. Okay? So then you may ask, what about the concept that on the top electrode there should be a counter charge that will be of equal but opposite sign from what's on the bottom electrode? You will ask that. All right? to answer that, I have to then tell you that in that sense, we're not talking about physical electrode, all right? I hate to use that term that I'm not asking to think about physical electrode. I really believe it is, but I have to ask you, but to answer the question where the charge is, I have to ask you to think it's not a physical electrode. What I'm asking you to think is this. Go back to the standard parallel plate capacitor. These are two metal electrodes, not MOS. Everything's simple, right? Right? I think you all agree with me that we can arbitrarily break the dielectric into two. Is that right? Yes? And reinterpret this one single capacitor as two in series. There's absolutely no problem. Is that right? Absolutely no problem, right? And if I ask you to say, try to think of this as truly a physical capacitor, an electrode, right? That indeed there is a capacitance between the top electrode and plane A. And there's a second capacitor between plane A and the bottom electrode. I hope you don't have a problem with that, right? That's fine. That's as electrical engineer, this is very, very useful concept. For example, if half of the dielectric is made of, let's say, silicon dioxide, the bottom is made of silicon nitride, this picture will be very useful. You have absolutely no problem saying it's made of two electrodes, right? Two capacitor, right? That there is something, there is a potential, it's very real as potential on these two electrodes. Now we can assign to plane A. Do you have any problem with that? That's made of two capacitors in series. So it's in this spirit that I'm asking you to think of the MOS as being made of two capacitors. Just as here, you can argue, hey, there's no charge on plane A. That's because the charge on plane A corresponding to the top capacitor cancels out the charge on plane A corresponding to the bottom electrode. Following what I'm saying? So therefore, in this surface electrode, there's no charge. But it's just as real, useful electrode as thinking about there was electrode at the interface between oxide and nitride. So we can think that there are two capacitors in series. Okay, so that's the electrode we're thinking about. So there's no charge at that surface, and the charge of the inversion layer belongs to the bottom electrode. Okay. All right. Good. So the surface substrate charge is the charge of the bottom electrode of the MOS capacitor. It's also the charge of the bottom electrode of CS. Okay? All right. Good. You know, I believe this concept you will find useful after you get used to it. You know, at the beginning, if you find it unfamiliar, don't worry about it. You'll get a chance to look at that you know, for a few weeks to come. So I think that will be fine. All right. Any questions about this picture? You know, I know you're all very familiar with the left-hand leg of this equivalent circuit, saying, okay, as MOS capacitor is made of an oxide capacitance in series with a depletion layer capacitance. Could you accept this addition? Yeah, that makes sense, right? MOS capacitance is made of oxide capacitance in series with the substrate capacitance, CS. And substrate capacitance is made of three parts, the inversion capacitance, the depletion capacitance, and accumulation capacitance, right? Okay. Right? All right. So, for example, in the most general case, we could actually write three capacitors in this equivalent circuit. Now, however, usually we can ignore one of, put it this way, C inversion and C accumulation are never important at the same time. You see, if we are in the inversion regime, then accumulation layer charge is always negligible. If we're in the accumulation regime, the bias into the accumulation region of the VG, then the inversion layer charge is always negligible. So those two will never appear at the same time. However, these two certainly can appear at the same time. And similarly, this two can appear at the same time. When will the right-hand side two appear at the same time? Oh, question first.
That was my question.
Okay, when will this left-hand side two at the same time?
Depletion.
It will happen at the transition between accumulation region of the CV and the depletion region of the CV. Isn't that right? So in the first order model, we also have a sort of a sudden change at this transition between the accumulation and the depletion. All right? It's a sharp change, even though it's not a discontinuity. But the second order of this first order derivative of this will be discontinuous. Is that right? Okay. So this is also what this new model can do to improve. Okay. We don't no longer have to think this is a sharp corner here. It's going to be a smooth curve, predictable curve. We have equation there. It's a long equation involving exponential terms of phi s, but it's equation there. So let's look at that. What is CS at Vg equal to VFB? Well, it turns out we can answer the question the same way that we did for the previous question. What CS is Vg equal to Vt? There is a complication, however, I'll tell you. Because of that complication, I will not work this out with you. You may find it interesting to work it out as an exercise, and then by all means do that. Complication is the following. At Vg equal to VFB, what is phi s equal to? Phi s equal to 0, right? Okay, let's remember. At flat band, the concept is that there's no band bending. All right, Vg equal to VFB, meaning we're flat band. At flat band, what is phi s? What is band bending at flat band? 0, right? Yes? So what you would do, of course, you will simply substitute 0 for phi s in the previous slide in the Cx expression. You substitute phi s with 0. Is that right? Right? You would think this is easy to do, except when you did that, you find out there's a problem. The problem is that numerator is 0 and denominator is 0. All right? But this is not a breakdown of this model. You all know that when both numerator and denominator is 0, not all is lost. What would you do? That's right. You take the differential of numerator and denominator, right? When you do that and you substitute the phi s equal to 0, this time they're not 0 anymore. And they will give you this, all right? So it takes a little time. I will not go through that with you. Is it okay with you? All right. So there's no new physics. It's just that we substitute the phi s equal to 0 into that expression, into the Cs expression, which is function of phi s. We get substrate capacitance at Vg equal to VFB. It happens to be equal to this, all right? And we wrote this in this manner because if we put phi epsilon s in the numerator, put everything else down below, then what is in the denominator must have a dimension of a length. Okay, and indeed it has the dimension of a length. We call that the bilength. Okay, you probably have heard of this term before, but I'll give you an interpretation. What the bilength is, it will help you remember it. The bilength, if you look at this and compare with that x depletion expression, you will see, all right? X depletion expression says it's equal to square root 2q, the band bending, called delta V, the voltage change across the depletion region, divided by, q is not here, epsilon s is here, sorry, divided by q na, is that right? Okay, again, it will take a little time to confirm this because we'll have a beta is equal to kt over q. Well, we will do it, all right? We will do it. Let's substitute kt over q here. Remember what beta is. Beta is 1 over beta is kt over q. That's what beta is. That's how we define beta. Beta is q over kt is beta. All right? All right. Now when you compare this with this, you will see they're very similar. There are a lot of common terms except for one thing. In fact, let's cancel out the common terms so we can see what we have to compare. It does not have this V. What is V is the band bending, right? Is V. So the bilength is the length of the depletion region corresponding to a particular band bending. How large is that band bending? It's as if we're dealing with a band bending of kt over 2q. Kt over q representing or replacing 2 delta V. So it's kt over 2q. Is that right? Yeah. So that's what it is. So if you bend the band by kt over 2, if you bend the band by kt over 2, if this is kt over 2, kt over 2q, meaning 13 millivolt, of course, right? If you bend 13 millivolt, That length is called the debye length. All right, sometimes called let's see, L sub d. Sometimes, all right, debye length. That's it. So if you have to write down or memorize this expression, just start with the depletion length expression, but change that V by kT over 2Q. All right, that's debye length. Now clearly this debye length is shorter with heavier doping and longer with lighter doping. So today with 10 to the 17th of doping, we're probably talking about debye lengths of 100 micron or so. I'm sorry, 100 angstrom or so. With lighter doping, it can be a few thousand angstrom, and that's certainly not negligible, right? Now, there are two ways to think about the significance of debye length. Maybe two things we'll think about. But in fact, this is very good to think about, use this at hand to understand the physical meaning of debye length. So think about what phi s is, CS is then. First, let's review what CS is in the classical model. In the CS, in the classical model, C is equal simply to Cox, which implies that CS is equal to infinity, right? So that the two capaciting series is the same as just one capacitor on top, Cox. That means the substrate capacitance is infinity, which makes sense because we would have said X depletion is equal to 0, right? So here we're saying it's finite. It's not. It's as if we have a finite thickness. Does that make sense? It really makes sense. What we're saying is that if we now, even if we have a flat band, if we now apply a small bias on the VG, apply small voltage, as a result, we apply a little delta VG. As a result, we will be applying a small delta phi s at the surface, right? Phi s will move up and down a little bit. Is that right? Under that condition, where do you think charge will be located? The way I drew this picture, you know, we have a little bit bending. Where's the charge? Of course, charge is somewhere distributed along this, you know, in this depletion region, right? Right? It's not right at the surface. No reason for it to be right at the surface. In other words, I'm asking you to visualize if you apply the voltage to the surface so that there's a little bending. As a result, you have a little charge. Is charge located at that plane of x equal to 0? No. There's this finite length, right? And that length is debye length. Okay? Okay. So another interpretation of debye length is that debye length is that uncertainty about where the depletion region ends and where the neutral region begins. Is that ranging, right? So we think this, KT over 2 region. How can we say there's not as much electron or hole as in the neutral region? You cannot say the band is hardly deviated from flat, right? We cannot say it's the silicon is depleted. That's another way to think about the debye length. So for example, if you try to determine, let's say, the doping profile using some CV technique, you'll never be able to quantify this doping profile within with a location accuracy better than debye length. So you always be off by a few hundred angstroms because we never know whether this depletion layer capacitance model is right, that charge is right at the boundary of the depletion layer, because we don't know where the boundary is. The boundary is a very gray region that's as wide as of debye length. That's another way of saying, all right? Okay? All right. So those are two examples how to use this new capacitance model, all right? Now, the important things to remember in general then, of course, is that it's very easy to know at the phi s equal to 0, what it is epsilon s over LD. At phi s equal to 2 pi b, we have figured out it happens to be equal to 2 epsilon s over xd max, all right? Two times, not one time. In between, we cannot give you a simple equation other than refer you to that exponential function, right? It's not too bad, actually. So in general, if you plot it, it's this shape, right? Specifically, when we are in the accumulation region, CS increases very rapidly. Okay, so interpretation is that inversion layer thickness become very narrow. The accumulation layer thickness is equal to LD, right at flat band. But as we go more strongly into the accumulation region, the accumulation layer becomes thinner and thinner and thinner. All right, never zero. In fact, later we even get a chance to see roughly how thick it is. Turns out it's about 15 angstroms, even in very strong accumulation. All right, so the CS just increases rapidly. Okay, similarly, beyond this VT, beyond 25B, CS increases rapidly because the inversion layer is contributing a very large CS. Inversion layer is getting thinner and thinner. Again, you can ask how thick is inversion layer. We can talk about it. All right. In fact, even today, right now, if you wanted to get a number for the inversion layer thickness, you can actually get it from CS. You just use that exponential equation that we derived today, get a numerical value for CS. From CS, you can figure out the thickness of the inversion layer. Does that make sense? Right? If the inversion layer truly is 0, CS should be infinity. The reason it's not infinity, meaning inversion layer has finite thickness. Right? You will be able to get the average thickness based on this capacitance. Right? And that is the correct concept. It's physically not accurate. We'll tell you why, because this analysis did not consider quantum mechanics. But this is still a very good introduction to the concept, the relationship between surface potential and the charge and the charge thickness. So I would like you to think this is not only correct, but even accurate. All right, there's a difference you see between correct and accurate. So it's not that accurate, but it's a correct model. All right, not accurate because we didn't solve Schrodinger equation here. But it's accurate. It's a correct model. So don't doubt its validity. All right. So that's what this curve is about. In between is the depletion region. Okay. In fact, I can tell you, you can even do this exercise in this region. The equation we gave you actually reduces to nothing but the depletion region capacitance. That would be a great exercise to do. All right. That equation reduces to depletion region capacitance. Okay. Any questions about this model? All right. And let's just look at a few diagrams, no equations here, just to illustrate a few points here. You know, we so far emphasized the capacitance versus phi s, and that's good. I hope from now on you will always remember that we do have a capacitance as a function of phi s. It's actually also good to remember that how we got there is that we actually first derived the QS versus phi s. You may have forgotten how that came about. QS is really nothing but d phi dx, right? There's epsilon somewhere. Let's not worry about that, right? So that's the equation we start with. We actually had a QS versus phi s. I don't believe that we have actually plotted the QS versus phi s for you. We just immediately differentiated that and got the CS expression. But if we plotted it out, QS as a function of phi s, okay? Today, if you look at one of the earlier slides, we do have the function. If you plot it, it's something like that, all right? Again, let me remind you what it is that it goes through 0 at the phi s equal to 0 point, flat band, no charge. That's correct. In the depletion region, this very much is just our Q depletion, very much like the first order model would tell you. Nothing wrong. Beyond the accumulation, beyond the VT, the charge increases rapidly. What is this charge made of mostly in this inversion region? It's the inversion charge, right? We'll call that Q inversion probably. We have not, may not have introduced that notation. Maybe we have. And similarly, in the accumulation region, the substrate charge increases rapidly and mostly made of Q inversion accumulation. All right. So this is also a good picture to keep in mind. And when we take the slope of this curve, we get the capacitance versus the potential curve. Is that right? It's okay? All right. Now what's missing, let me tell you, and that's what we will do next time, is to try to figure out how to change from this axis phi s to this axis to Vg, how to make that change. Is that right? How to change from Cs to total C, the gate capacitance Cg is trivial. We simply put the Cs in series with a constant Cox, yeah? Then we end up with a total capacitance Cg, right? This change is not so trivial, so we'll talk a little bit about that next time. All right? Any questions about what we discussed today? Okay, so we can do that, and if you like, you can also think a little bit about how you would make this change, transition between phi s to Vg. Okay?